Hello, I am Tatiana Didenko, and I work in the structural chemistry group at Amgen. So as it may be obvious, we help the medicinal chemistry group by providing in-depth NMR characterization of small molecules. However, apart from individual requests, we also maintain high-throughput NMR measurements for structural characterization, where ideally everything should be automated. So here I want to present our current high-throughput NMR spectroscopy setup and our latest improvements in data storage. At this slide, there is a scheme which shows our approach at Amgen to generate compound libraries. There is a highlight of two steps which are done by our separations group, and we, as an NMR group, we collaborate directly with them. In the bottom of the slide, it's shown what exactly they do. So they perform mass-directed automated purification of crude reaction mixtures, and in the end, they get two vials, a product vial and a bioassay vial with the purified compound, and also two plates for quality controls, an NMR plate and LCMS quality control plate. The data obtained during LCMS and NMR is required for compound registration. At this slide, it is shown in greater detail what exactly happens during the purification step and which equipment is used. So, as I mentioned before, in the end, two plates, two 96-well plates are generated. They're shown here. We work directly with the NMR plate, NMR plates, which contain the dried product. We dissolve the powder they provide us in deuterated DMSO. Then we seal those plates and initiate NMR measurements. Just a couple of words about our NMR setup. We use Flow-NMR technology. We set it up in collaboration with the proteases company. We have a cryoflow cell, which has about 30 microliters of active volume, and the sample is delivered automatically. The magnet we use currently is 600 megahertz Bruker, which is equipped with the cryo platform. And we use 1 minute NMR software by proteases again, and it works together with Topspin software installed at magnet computer, which was made by Bruker. And our group has presented several times the NMR hardware and software we use, so I'm not focusing on that today. But if you have questions, let me know. So today I'm mostly focusing on how we handle the data and distribute it. So when we get this NMR plate with dried compound, when it is submitted to us, we also get an SDF file along with the plate. SDF stands for structure data file, and it contains all the information about each compound. For example, the sample ID, which corresponds to a chemist's lab book page, chemist name, and structure of the molecule in the mol file format. NMR plate produced by separations group usually, but not always, contains several samples. So this structure data file for each sample is combined to the SDF file for the whole NMR plate, and when it happens, a specific well is being assigned and indicated in that file. A plate gets an ID and a barcode, and it is printed and attached to the plate, and it's readable by a reader. When the reader scans the plate's barcode, this SDF file associated with the plate is transferred into 1 minute NMR software, which in turn generates a sample queue. So It is quite a flexible software. It's possible to actually choose an appropriate experiment set and vary number of scans, for example. Usually the experiments we measure are either carbon-proton HSQC and 1D proton NMR, or carbon-proton HSQC, proton-proton COSY, and 1D NMR again. Everything, so 1 minute NMR software communicates with the topspin software installed at the magnet computer. Everything is measured in topspin, and raw NMR data is stored under the sample ID name, and processing is performed automatically at the ACD automation server, and then the data is dispatched to the chemist. I will just show the whole slide. So this slide actually shows how the processed and raw NMR data was distributed and stored until recently, and which problems we experienced. So the data would be stored in a folder which belongs to a certain chemist who, for example, submitted a compound for purification and characterization. The results were stored as Spectres projects and as PDF reports created by ACD, and all in separate folders. Raw data was also kept separately. Basically, there were a number of folders with subfolders at some common shared network location. So we used this setup for a while, and while it didn't cause any catastrophes to my knowledge, there were apparent imperfections. So the biggest one is that the data were not mineable. It was not possible to perform an actual search, a structure-based search, for example. And one had just to go through those folders to get some information. Also, there were some potential security problems because anyone who had access to the shared folder could edit this data, and no consistent backup was really performed. Also, it is shown on the slide that LCMS was not connected to our NMR measurements, and the results were stored separately. But in 2020, we actually launched a unified database, so-called UDB, which is supposed to solve all the problems indicated in the previous slide. Our actual experimental workflow stayed the same, but the resulting data, such as spectra themselves and analysis, are now combined in the database. So there are no separate folders anymore. The database also has an option to edit the data with Spectre's processor. Therefore, the entries are editable. And each compound would have an entry containing all the relevant information in a searchable format. Also, as you can see, the LCMS data is also stored in this database. Therefore, each entry will contain both NMR and LCMS results. Here on this slide is the summary of the unified database organization. And first, there is, as I mentioned before, there is one location for all small molecule analytical data, and LCMS and NMR data is integrated now. Along with the searchable option, it really improved the sharing options across the organization. Also, I must note that the data comes not only from the high-throughput measurements, which we organize, but also from open access instruments. Therefore, chemists can obtain the data themselves, and it will be also submitted to the UDB. On this slide, here are some of the advantages of this improved data storage. which we didn't have those advantages before with our old setup. So now you can basically just approach data more comprehensively, like seeing which spectra you obtained in a specific period, for example. And if something is wrong, the data is editable by an approved person this time, as the chemist. If, for example, there is an obvious misassignment or picking error, one can edit the spectra and save the correct entry. And one of the great features is that the data is searchable by structures and even substructures, which may help in many ways. For example, we can use it as a tool to look at spectra similarities if we have problems with the assignment. Okay. Also, the nice thing about the database is that it is accessed through a browser, the Citrix environment. So there is no need to install software now, and one just has to be in the Amgen network to employ all the power of ACD processing. So here is an example how the browser access via Citrix environment looks like. Once you log into the cloud, your personal screen, it's in the bottom, it has either access to the database, SpectresDB, or to the Spectres processor. It's all in the cloud. And notably, that's not the only option. And of course, if the software is installed on your computer, you can access it, the database, through the desktop software. But Citrix version, the browser version, is actually it can be faster because it is located in the cloud. This is an example of the data stored in the database, and here is an example how the data is searchable. I told before that this is one of the main advantages, and this is an example of how data search looks like in the UDB. And there is an extensive number of ways to look for the data there, and there are also logical operators. Here is not a very common search shown, so one can look for data obtained on a particular NMR probe, reading the parameter file using the probe HD, and in a specific time slot at the same time, like later than July 2019, and it indeed added a lot of flexibility. Here is an example of LCMS view, how it looks like. So it contains the structure in the left and all the data in the window below it, and the spectra in the right. And one can actually edit the data. Here it's shown a reintegration, for example. So one opens the data which needs editing in the processor, introduces corrections, and then it is possible to update the database shown below and update reports. Here we have the NMR view. Also, the structure is shown on the left with all the necessary data below it. And notably, there is also a link to a PDF file, to a PDF report, which was created automatically by ACD. And as you can see, there is an option to copy this report to the electronic lab notebook, to the electronic lab notebook, which chemists actually can initiate themselves. It is possible to set it up so that the reports go to the electronic lab book automatically, but it seemed more convenient to chemists to initiate this synchronizing themselves. Therefore, there's an option created. Here's an example of how the report looks in the electronic lab book, which our chemists have, which contains all the synthesis information, for example. And basically, it is added to the sub-pages in the PDF format. And here it is the automated structure verification report created by the ASV protocol. So actually, this convenient synchronization with the electronic lab books greatly supports data integrity. Here are some points are indicated. So basically now it's well, more organized, and it's easier to trace the data and locate it by anyone who is interested. The actual data actually is also more secured. So with this database approach that we use now, the automated structure verification analysis became even more critical. We did use it before, but now it actually has additional useful features for us. So let's say the proposed structure has a weak score based on NMR data we obtained, which is a potential problem. First, it could be, for example, a problem with processing. And for example, if there is a strong solvent signal or overlaps, and it can easily, in this case, be corrected in the Spectrus processor. Also, one can look at the LCMS data to check if something is obviously wrong there. And finally, if similar structures have weak scores, it could be due to imperfections in the verification algorithm, and then this weak score can be neglected. There is also one great option now, a combination of the automated structure verification protocol and database approach. It now provides a possibility to perform structure verification for all the samples in our sample bank using 10 millimolar stocks in protonated DMSO. Those samples just get dried, redissolved in deuterated DMSO, and then measured. The data is submitted to the UDB entries created for these samples, and it is now easy to access them based on the ASV score. So we do use the ASV routinely, and now it actually has even more useful features for us. Here's an example of how ASV actually correctly assigns complex structures using just HSQC and 1D experiments combined. There is a lot of nitrogens in this structure. However, it was verified quite confidently. Here's another example of how ASV assesses complex structures using just HSQC and 1D experiments. Was quite confidently verified by ASV despite this enormous size and even some overlaps. Nevertheless, although HSQC and Proton-NMR work fine with the automated structure verification protocols, we actually introduced NMR supersequences to improve structure verification even further. So those supersequences are widely known in the NMR field now, and the idea is shown on the left. So is to utilize the same recovery delay, which is usually quite long, and the same initial monetization to record several spectra. For example, here it's shown that with the same recovery delay, D1, HMQC, HSQC, COSY, and NOSY are recorded at the same time. So those super sequences are quite common now, and it's possible to get them from Bruker online library, for example. So in the right, it's shown that, for example, we have it integrated in the 1 minute NMR software. It's possible to choose it if, for example, we want to measure super sequence. Here it's HSQC COSY option is shown. We employ those long supersequences shown in the left in our Flow-NMR setup very rarely. However, I, for example, had cases when 10 millimolar samples from sample bank were submitted for more comprehensive structural elucidation, which would require, for example, NOSI and even HMBC. And while it would take a long time to record those spectra conventionally, it was possible to get some meaningful structural data in a few hours using supersequences. Nevertheless, we mainly use HSQC and COSY combination, and because those types of spectra are also processed by ASV protocols, and the reports are generated as always. Yeah, this is on the parameter file. So here is an example of how our HSQC COSY spectra processed by ASV, and here it's shown the COSY proton-proton COSY, how it's processed by ASV and how it potentially can improve assignments. You see the correlations are shown quite clearly, and there were cases where COSY indeed helped to resolve some assignment problems when the proposed structure had a low score. So I must say actually that in the case of HSQC COSY combination, it's not really vital to use a super sequence because proton-proton COSY is a very sensitive experiment, and HSQC and COSY could be recorded separately in almost the same amount of time as HSQC COSY super sequence. I have already mentioned that using the ASV, the structure verification protocols, we actually can check all the samples from our sample bank, which were already submitted. And we can either confirm the structures or find out that there may be something wrong. And also, it is possible to see if the compounds do survive storage or something happens to them. Here is the representation of the process. So we call it high-throughput quality control, HTQC NMR. And it differs from our standard routine only by the necessity to replace a solvent, the wet DMSO with the deuterated DMSO. Otherwise, everything is the same. There is also quite a notable potential problem with those samples because they have very low concentration. The resulting concentration that we have in the end is like maybe 5 millimolar. However, it is still possible to record meaningful spectra and get nice results. Here is an example run of such low concentration samples at our Flow-NMR setup. So on top, it's shown how the sample was actually prepared, and the spectra actually looks good. And the ASV algorithm verified the structure correctly. So as I mentioned before, it's also possible to increase the number of scans in 1 minute NMR, and if the time is not a limited factor, then it just can record more scans for such low concentration samples. Okay, so here's the list of advantages of this HTQC approach. It again is quite valuable in a combination with the unified database approach, because ideally all of our samples which are submitted already, they could be processed by NMR, and it will create a massive amount of NMR data linked to actual structures. So apart from obvious use, this data can be employed in machine learning algorithms to improve structure prediction, for example. All right. So here I presented an overview of our high-throughput NMR methods, which we use routinely. And I want to thank you for your attention. And please let me know if you have questions. Thank you.